So we'll get started. So did you have any questions about the, did I give you your test yet? My bad. I thought I did. And then it occurs to me I did not. So if you're not here and you'd like to get your test, well, I don't know. Come to class to get your test then, I suppose. Otherwise, it will sit in my office. Now, I'm not entirely sure because these weren't stapled. So you might want to check and make sure these are all yours. Are these all yours? Oh, that's mine. So do you? So if you want to, you can just kind of look at my solution for the moment. So I will be posting the solution to test 4 here sometime soon, hopefully today. Don't worry. Rational functions will come back for the final. You'll have another chance to, right the wrongs that happened, whatever they might have been. But next up, we're talking about radicals. So this is Chapter 6. I don't remember right offhand if Chapter 7 is also on Test 5 or if Chapter 7 is just on the final. I can't remember right offhand, but we'll figure it out before the time comes. So do you have any questions about the test? Or?
Just careless mistakes.
Nah. Yeah. You're not a politician, so none of your mistakes are on purpose, but well, it's hard for me to judge because people haven't written all their work on this test, so it's hard for me to give partial credit when I don't have work. Anyway, I do intend for more of the questions to be short answer. This was all multiple choice, obviously, but I would assume that there will be less multiple choice and more short answer on the final, so you'll maybe have a little bit better chance in that regard. Okay, so let's get to it here. The symbol is a radical. And this is the square root, okay? This is the square root symbol, right? We also have, well, let's see here. It says the expression written with a radical is called a radical expression. The expression written under the radical is the radicand. So let's see here. So we could have something like the square root of x plus 3 equals to 2. Well, this would actually be what? This would be a radical equation, right? Right? This would be a radical equation. It's not an expression. It's got an equality. What's the radicand here? Right here, this would be the radicand, right? The radicand is the thing you stick into the radical. Radical expression could be something like this. The square root of 3 plus the square root of 7, plus 8. There you go. This would be a radical expression.
So the 8 is supposed there's the radicand.
That's the radicand. Here, the radicand is 3 in that one. Here, the radicand is 7. All right. Now, we can also talk about the index. So these are so far everything here is all square roots. All right. You can also talk about the, let's say, nth root of stuff. All right. There, use a technical term. So again, still the radicand is whatever goes into the radical, and here n is called the index. The index. So our default is that the square root, what's the index for, so like this is a shorthand for this, all right? We just, square root is what we're most interested in, so we don't adorn it with the 2. The index is understood to be 2 for the square root. Okay? So just some terminology. Now let me stop this terminology business and let's look at some actual how it works and how to calculate with it and all that. Yeah? Okay, Race? Okay. So what does it mean if we say that the square root of x equals to, let's say a. What does that mean? This means that a squared, right, is equal to x. And a is greater than or equal to 0.
Oh, this is that section.
Yes, this is that section, right. Now, on the other hand, if we have the nth root of x equals to a, what does that mean? That means that, well, then we have to break it up into cases, okay? So we have n even, and we have n odd. All right. For even n, this means that a to the power n is equal to x, and a is greater than or equal to 0. All right. So even roots are assumed to be non-negative. On the other hand, odd roots, no problem. You can have the nth root of a just implies that a to the n is equal to x. We don't have to assume that a is greater than or equal to 0, right? Let me show you some specific numerical examples to sort of expand on what I'm saying here. Yeah? So, the square root of 25, right? It is equal to 5. Since 5 times 5 is what? Is 25. And, of course, 5 is greater than 0, right? It is also true, right? It is also true that minus 5 times minus 5 is equal to 25, right? But we do not say that the square root of 25 is minus 5, despite the fact that minus 5 squared is 25. All right? That is our convention. The square root is the positive root. Or 0. If the square root of 0 is 0. Example 2. If we calculate the cube root of 8, can see that that's 2, since 2 cubed is equal to 8, right? But we can also calculate the cube root of minus 8. And the cube root of minus 8 is negative 2. Since minus 2 cubed is minus 2 times minus 2 times minus 2 times minus 2, which is minus 8. Oh, so the cube root of a negative number is a negative number. And what's that? So I think the other thing we should talk about here. So that's the basics, right? So let's talk about how to simplify things involving, I mean, in some sense, right? The square root and the square, they're inverse operations, right? So let's see how that goes, right? We have, suppose we look at the number 3, right? We square it. What do we get? We get 3 squared, which is 9, right? And then what? Take square root. What's the square root of 9? It's 3, right? So we're back where we started, right? So, but on the other hand, if we take minus 3, right? And we square it, we get 9 as well, right? And if we take the square root of that, take the square root of that, what do we get? We still get 3, right? So when we take the square root of a square, right? What do we get? We take the square root of a square, what happens? See, on the one hand, we have the square root of 3 squared is 3, right? But we have the square root of minus 3 squared is also 3. So the answer here is it's equal to plus or minus a. When is it plus? When is it minus? It's plus when a is positive. It's minus when a is negative. We have another name for this function, right? This is, to be more specific, this is the absolute value of a. So the square root of the square is the absolute value. In contrast, though, there's an asymmetry here in how things work. Notice that if we take the square root of, let's say, b, right, and we square that, then that is by definition b again. So squaring a square root doesn't bring in a plus or a minus, right? But taking the square root of a square does bring in a plus or a minus, depending on whether or not the thing being squared is negative or positive. Now, the same story holds for any even root. Okay, so like for any even root, we still have, if you take the nth, let's say, I'll put it in n even, right? We take the 2nth, good grief, the nth root of a to the n, guess what? We get the absolute value of a. But it's also true that the nth root of a, of b rather, raised to the n power is b again. So absolute value when we take the nth root of an nth power, but we just recover b again when we take the nth power of an nth root. This is essentially just the definition of the nth root. What is a square root? It's the number, whatever the square root is, it's the thing that you square and it gives you the radicand back again, right? So like this is just the definition of square root. On the other hand, n is odd. When n is odd, it's easier. You just do like, if n is odd, you just have that the nth root of a to the n is a, and the nth root of a, of b rather, to the n power is equal to b again. I mean, so there's no, when n is odd, it just, you can be careless, yeah. All right, so that's the tricky. I'm starting with the tricky part, yeah. This is actually the trickiest thing in this whole silly chapter, honestly. So let me just put that into practice, yeah? Oh, I guess I wasn't actually out of frame. It's almost out of frame. Well, maybe I was. Okay, so example 2, right? And I'm jumping ahead a little bit, but I want to emphasize why this matters, yeah? So you want to solve x squared equals to 16, right? So when we take the square root of both sides, right? When we take the square root of both sides, what happens? See, because I have the square root of a square, I have to put the absolute value of x. Square root of 16, that's 4. So what this gives me is plus or minus x is equal to 4. But of course that gives us x is equal to plus or minus 4, right? So what's a shortcut I usually use in these kind of problems? When I take the square root of x squared equals the square root of 16, what I say is I just go immediately from that to x equals to plus or minus the square root of 16. Because I'm after x, right? So, and of course that's the answer, right? Let's contrast it with a cube. What if I was calculating x cubed equals to 7? Right? Then if I take the cube root of this equation, the cube root of x cubed is the cube root of 7. Well, the cube root of x cubed is just x again, okay? And so this gives us x equals to the cube root of 7. And that is the answer. Now, what is the cube root of 7? 1.1, what did you say? 1.91. 29 stuff, right? 31183. So yeah, you know that is an irrational number, right? That's not a fraction. It doesn't have a repeating decimal. It goes on and on. All right, so you see the difference. You see why this matters? I mean, it matters because when we're simplifying radical equations, if we're taking an even root, we need to allow for plus or minus. If we're taking an odd root, well, you know, it's easy. Of course, this also is necessary for solving some of the problems in section 6.1, I suppose. Let's see here. So let's see here. For example, let me just do a couple examples here. Can I erase?
Yeah.
Okay. Example 4. This is like number 71 from section 6.1. We're told A is any real number. Simplify the following, okay? The fourth root of 5a to the fourth power. All right, so I suppose at this point I need to show you, I need to like mention some of the properties of the radical, yeah? So in order to solve this problem, I need to show you some more, I need to give you some more tools, don't I? So properties, props for radicals. So we have the nth root of a times the nth root of b is the nth root of ab, and the nth root of a over b is equal to the nth root of a over the nth root of b. I think those are important to know. Let's see here if there's any others we need at the moment. Well, I don't think those are in this section of the book. Oh man, really? Dude. Not cool. Not cool at all. So you would like to know these properties in order to solve this homework problem, I think. And so here's why this is true. So if we have, if you let the nth root of a, let's call the nth root of a equal to x, and the nth root of b equals to y, okay? Then if we have, this means that x to the n is equal to a. This means that y to the n is equal to b, all right? So then we have x to the n, y to the n is equal to ab, which tells me that xy to the power n is equal to ab. All right? Which then tells me that the nth root of ab is equal to xy, which, by the way, is equal to the nth root of a times the nth root of b. And so there's the property. I don't do too many proofs in here. I mean, it's pretty rare, right? But what I'm doing right now is proving why this is true. So why is the nth root of a times the nth root of b the nth root of a times b? So let me just walk us through it. Number one, if the nth root of a is x, right, and the nth root of b is y, what does that mean? That means that x to the n is a, right? and y to the n is b. That's what we mean by nth root. So I'm inventing x and y as intermediaries to understand why this is true, okay? And so then if I multiply x to the n times y to the n, I get a times b, right? But by properties of exponents, x to the n times y to the n is xy to the n, right? But what do I have? I have that the nth power of xy is equal to ab. What that means is that the nth root of ab is equal to x times y. But x times y is the square root of n, the nth root of a times the nth root of b, and there you have it. So that's why that property is true. And I was looking in your book, that's actually not in section 6.1. This property is not in section 6.1, but they've given you this homework in section 6.1. That's not cool. You need this property to do this homework problem. See, because, at least I think you do. Oh, I guess you don't. Dang it. I'm a moron. I'm an idiot. Like, you could just look at this directly, right? What would this be? I'm sorry, I'm a dummy. I didn't need the property over here, because I could have just done what? This is it's the fourth root of something to the fourth power, right? So that's the absolute value of 5a. Okay? And that is 5 times the absolute value of a. I see. Okay, fine. They didn't need the property yet. But you would have needed the property if you had been so foolish as, like me, to write this instead as the fourth root. What I was thinking in my mind is 5 to the 4 is 625. A to the fourth, yeah? And so that would have been, the fourth root of 625, and then the fourth root of a to the 4. Of course, I'm just being dumb. This is 5 to the fourth, yeah? So the fourth root of 5 to the fourth is 5 again. And so you still get the same answer, It's just, I wanted to make more work of it. My bad. Here, let me make up an example where I have an excuse to use my proposition. Example 5. Okay, suppose I'm calculating the fourth root of 3 a to the 8th over, 16 b squared. Let me make that 3 become like an 81. 81 would be more fun. So if I use my properties of radicals, this is the fourth root of 81 times the fourth root of a to the 8th over the fourth root of 16 times the fourth root of b squared, yeah? I don't want b squared there, I'm a dummy. B to the fourth is what I meant to put there. I'm sorry. B to the fourth. So what is the fourth root of 81? What is 81? 81 is 9 times 9, right? Which is 3 to the 2 times 3 to the 2, right? So 81 is actually 3 to the fourth power. And so what is the fourth root of 81? It's just 3. So we get 3. And what's the fourth root of a to the 8th? It's the, I guess I should have written that a to the 8th is like, a squared to the fourth? Yeah, we could do that. A squared to the fourth. So then that would give me 3 times the absolute value of a squared, right? And downstairs, what's the fourth root of 16? Well, 16 is 4 times 4, which is 2 squared times 2 squared, yeah? which is 2 to the power 4. So see, this fourth root of 16 is 2. So I get 2, and then that's absolute value of b. So that's a good answer, but the absolute value and the square are interesting. So what's the absolute value of a squared? Versus what's the absolute value of a squared? See, this is plus or minus a quantity squared, right? Which is, by the way, a squared. But if you think about it for a minute, you'll see that you could simplify this to 3 times the absolute value of a squared. So like think about it this way, if a was like minus 7 squared is what? It's 49, right? Absolute value of 49 is 49. Absolute value of minus 7 is 7. 7 squared is 49. Whether you take care of the minus in the square, or if you take care of the minus in the absolute value, either way you end up with the same answer here. So you can pull a square outside an absolute value like that, for what it's worth. And this is also interesting, like the absolute value of a square. Oh, look at that. So I could simplify that further, right? The absolute value of a... So this is also equal to... I could just write it as 3a squared, come on, over 2 absolute value of b. So there's, you know... But on this kind of problem, I would be like pretty happy with you if you just gave me that as the answer even. Yeah. So... All right. One more of these and then I'll move along. Suppose we have example 6, remember. What if we have the fifth root of x minus 1 to the 5th power? How does that simplify? But this is an odd. See, 5 is odd, so easier. It's just... you got me writing it. You fished me in. I'm apparently very impressionable at this time. I could drink some coffee or something. I don't know. So it's just that. Yeah. Okay, so let's move on to the next section here. Yeah. So in the next section, we talk about the exponential notation. So there's exponential notation and there's radical notation, all right? So exponential notation for the nth root of a is a to the 1 over n. Okay, so the nth root of a is a to the 1 over n. So for example, like the square root of 7, we could also write as 7 to the 1/2, all right? And we also have some nice nice rules. We can also have this. Here's a rule of algebra for you. The nth root of a to the m is equal to a to the m over n. Yeah, sorry, let me make it weirder. P there. And so in other words, a to the, let's say, p over q means what? This means the qth root of a to the power p, right? And we can also talk about a to the minus p over q. What would that mean? This would mean 1 over a to the p over q, which you could also write as 1 over the qth root of a to the power p. Or you have choices, right? You could also do it, I should mention that this could also be written as the qth root of a to the pth power, I think, is also true. So, I mean, what I'm trying to say is, here's the way I think about it. If I have a to the p over q, I can either think about that as a to the p times 1 over q, right? Which suggests to me a to the p to the 1 over q, right? Or I can look at it as a to the 1 over q times p, and I can look at that as a to the 1 over q raised to the p power. So this one would mean, in terms of radical notation, the qth root of a to the p, whereas this one, in terms of radical notation, would be the qth root of a all to the power p. And those are equal. So the main rules that we have to work with here are these. A to the s times a to the t is equal to a to the s plus t, and a to the s divided by a to the t is equal to a to the s minus t. And then this one, a to the s to the t power, is a to the st. So these are the laws of exponents, yeah? Or laws of exponentials. Let's work on one of these, yeah? I should mention, all of this assumes that A is positive. If A is negative, bad things happen to these formulas, okay? Yeah? Like A is negative, it's not gonna go well for us, okay? Here, let me do one of the examples in the book. 64 to the minus 2/3 power. What example am I on? 8? 6? 7? Ah. It feels like an example 8 to me. I could be wrong. But let's simplify 64 to the minus 2/3, okay? Like I could just plug that into my calculator. That is true, but it would rob us of the experience we would get from applying these things to a number as opposed to just some letter soup, right? So let's not steal the joy. I see you with that calculator. God didn't make calculators. Calculators are the devil. Prince of the power of the air. No, sorry. I once had an old professor substitute for me when I was at Liberty. Like the first year I was there, I had this college algebra section with like 80 people in it. It's huge, it's horrible. It had a board that was like a third the size of this with an 80-person class in a dimly lit room. It was horrible. Anyway, I was sick, and he was like covering for me, and I heard there was a girl right in the middle of class. She got out her cell phone to like check Facebook or whatever students check at that time. It's 10 years ago, you know. And he told her, "Put that away. Those are from the pit of hell." It's like, I don't know. I don't quite take that approach, but his direct approach with students, it always amused me. He was from Texas. He used to have a lot of like very weird sayings that you'd only hear in his classes. And he would also like, you wouldn't be safe as a student. Like if you went to one of his classes, it didn't matter who you were, he would just like call on you in the middle of class. Like you couldn't just kind of like be passive in his class. Like he would harass you. So I've never really taken this approach. I mean, certain students I will harass, but they're in kind of short supply at the moment. But so we can either look at this, right? You got so minus 2/3, right? So that means that this is 1 over 64 to the 2/3 power, all right? And then we can either first do the square or first do the cube root. I don't want to square 64, so I'm going to do the cube root first. So this is the cube root, right, of 64, and then we square it. What is the cube root of 64? Four, right? Because 4 times 4 is 16, and 4 times 4 times 4 is 64. So the cube root of 64 is 4. 1 over 16, right? Yeah, I did all that. You just put it in the calculator and had it just like that. Yeah, that is true. You got me there. I mean, I guess I don't know. It's like I see these cross country athletes around here. You know, they're all running in circles all day long. You know, to get from point A to point B. They could just call an Uber. You know, why are they running? They could just get, you know, call up a ride and skip the whole running, you know. I don't really have any proper rodeo analogies to like make it more real to you, but I'm sorry about that. I'm just fresh out of rodeo analogies. I don't have any. Here, example 9. Suppose we're calculating the 4th root of, or the 8th root. Ooh, 8th root, exciting. 8th root of a squared b to the 4th. And so here, the instructions are to leave the answer in exponential notation. All right, convert to exponential notation. Simplify to exponential notation. Okay. So let's use the property of radicals that I proved without need in the first section. This is the 8th root of a squared times the 8th root of b to the 4th, yeah? And then, what is that? That's a to the 2/8 and b to the 4/8. And so we can simplify those fractions, right? That's a to the 1/4 power and b to the 1/2 power. Again, assuming that a and b are positive here, right? And so that was the simplification into exponential notation. What would the answer be in radical notation? See, in radical notation, this is what? The fourth root of a times the square root of b. So that's kind of neat. All right. So I know students have a lot of trouble with these sections, right? These require a lot of care, and it's easy to get these wrong. I don't know why, but like people struggle with these. If there's anything that like my beginning calculus students are just completely inept at, it's this stuff. It's just picky, but it's nothing you guys can't learn. So, you know, just do the homework, do it carefully. Don't rush through it. Try to make sure that you're finding whatever it is you got wrong in your head about these things as you go, you know. And I'll try to work a bunch more examples from like section 6.2 next time we meet. Although I may be talking to myself. If I need to, I will. See you guys.